Okay, so throughout this course, we've talked about transformations from one vector space to another. However, what if we want to transform not only from the second vector space, but to a set of all real numbers? So, by first representing that by a diagram, we'll call this vector space V, call this vector space W, and let's define a transformation, call that alpha, which is the transformation from the vector space V, vector space W, and that's represented by this arrow for alpha. And then if we want to perform another transformation, a set of all real numbers, well, we can define this transformation as T, which is the transformation from the vector space W to R. And for any vector in this vector space, we can represent that by a dot for vector V. When it transforms over here, that we represent it by alpha of V. And when it transforms over to here, when we apply this transformation to this vector, we'll get T of alpha of V. But suppose if we want to take a different route, well, if we want to apply this transformation to get the same thing, well, this would be the composition of the transformations T and alpha. And this is one specific example of a linear transformation. However, what we can do is define a set that contains all the linear transformations, all these transformations from this vector space, the set of all real numbers. But we can call that V star for the moment, and that's equal to the set of all transformations from V to R, such that T is a linear transformation. Abbreviate that statement. And of course this transformation, not the same as this one. This transformation here, from V to R, is this composition, all the compositions. And not only is this a new set that we can define, this is also a vector space. So V star is a vector space. And the way in which that can be proven is just by writing out the closure axioms in particular, showing that the properties of vector addition and scalar multiplication are not violated in a sense, or they still hold true for this vector space, and that the zero vector exists. So, and the vectors in this vector space, they're commonly called covectors, for instance, and what we can also do is, since we've also defined a new vector space, we can also define another transformation with relation to our original example here. And we can call that alpha star at the moment. And this transformation will be represented from W star to V star. Well, the appropriate name for V star is the dual vector space of V. And of course, this dual vector space, with this definition, can also be applied to a general case, of course, for any other vector space, because the dual vector space of W is all the transformations from that space to the set of all real numbers. So this definition of this new this new transformation is consistent with these operations. So another thing to note is that the name of this transformation is called pullback map. And we like to think about with it being called a pullback, is that as if you're kind of taking a step back and going in a different direction. And alpha star, for instance, is just we can also call that the pullback function. And it's also a linear transformation. And the way in which that can be proven is, of course, by showing that addition and scalar multiplication do apply for this transformation. And we can also rewrite this in another format, which it will be written as such. It should be the pullback of t by alpha. And, however, these two statements are equivalent to each other because this represents this transformation. So now that we've defined a new vector space, which is the set of all the linear transformations from this space V to this space R, and we found a new function. Well, of course, this has it anticipates many other different things. But another thing to note is that we can also move on to multilinear mapping multiple, or the Cartesian product of all pairs of vectors to another vector space. But to begin with that, let's say if we have a set of vector spaces, V1 through Vn, where their Cartesian product is defined as a set for all pairs V1 through Vn, Vi is an element of the vector space Vi. Of course, each respective vector in place of this Cartesian product for this order, for the Cartesian product. Well, this set can also be proven to be a vector space. And we can, of course, again, we prove that in a very similar fashion to proving that the dual vector space of some vector space is also a vector space. So, moving on, we can also look at a transformation of this set, also assuming that we proved that it's a vector space as well. We transform from that set V crossed to Vn to some other vector space W. Well, this transformation is multilinear if each component, i.e., each operation of addition and scalar multiplication in this transformation, is linear. Okay. Also, if each Vi in this Cartesian product are the same, for instance, if we have a multilinear transformation, V cross dot dot cross V, and the vector space W is in fact the set of all real numbers, this transformation is called the multilinear in form of on V. By meaning in form on V, one particular example would be the bilinear form or bilinear mapping. And of course, that corresponds to our next example. For instance, if we have transformation of T V cross V to the set R, this is known as a bilinear mapping, by taking, of course, an ordered pair of two vectors and then transforming that over to the set of all real numbers. And an example of a bilinear mapping would be the dot product. For instance, if we define that transformation as epsilon, or that is the transformation Rn cross Rn, that's transformed to the set of all real numbers, and that would be given by two vectors u and v, where if vector u, that equals u1 un, and vector v equals v1 through vn, then defining this as a dot product, we would have u1 times v1 plus all the way to un times vn, a particular example of bilinear mapping. Well, a bilinear form of a linear transformation anticipates our next topic, which is symplectic forms.